we can imagine that there are spaces in here, that this isn't absolutely densely packed. And if that's the case, then I take this out of a vacuum into air, and the moisture in the air can go down in those pores. In the case of magnesium fluoride, this became obvious many years ago, where the structure might look like this. And there was a paper published, I recall, where somebody had mag fluoride in a coating chamber and were able to measure essentially its index of refraction, and as deposited, we'll say it was this index of refraction. And when they opened the chamber, the index increased because it was pulling in this water vapor in those spaces. And then if they pumped it down again, the index decreased as they pumped away some of the water. But it never got back down to where it started, meaning that some of that water was grabbed and stayed there and could not be pumped out in a vacuum. Now, possibly if it was heated up again, it might drive off that water. Don't know. But if you had any chemistry, which I think most of you have, you could look in the Handbook of Chemistry and Physics and see that they've got such and such a crystal dot H2O. Means that crystal has attached with it, almost as part of its crystalline form, some water. And so I think that's what this permanent water absorption is. So as deposited, a porous film has a low index, and then in atmosphere it increases quite a bit, and then when I pump it down again, it'll go down, but not all the way. So these are the kind of things we've seen evidence of. Now, if the index of refraction changes, the spectral curve is going to change. And this became particularly important when we started to try to make laser high protection filters. Because if we had a filter that blocked this laser line, but then humidity shifted so it then passed the laser line, all of a sudden somebody's going to get their eye damaged. And so we've got to avoid that. So the specifications on laser eye protection filters are that they should work at high humidity, low humidity, et cetera, et cetera. Now the specification back when I was working with it, and I suspect it's probably still the same, had something about thou shalt put this in a 90% humidity chamber at 90 degrees Fahrenheit for 24 hours, and then measure it, and then put it in a zero humidity at 100 degrees for 24 hours and measure it, and get the humidity shift. That takes a long time, blah, 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 whatever it was. It was like that. Well, I said, nah. And we were developing these kind of filters, and I wasn't going to wait to do that. I needed to know now what I need to do to change my process. So what I did was I would take a filter out of the coating chamber, and I'd go under the faucet with a brown paper towel, and I'd get this thing soaking wet. I'd wrap it up in the towel, which was damp, and I'd go over to my spectrophotometer, and I will have run a 100% line and a 0 line, and I open up the cover and I put this wet part in. It's got no visible water now, but it's 100% humidity. And I put that paper towel, which is damp, down at the bottom of the chamber where the beam doesn't see it, close the cover. So That's my approximation of 100% humidity. And I run the spectral curve. And then I'll pull the wet paper towel out of there, close the cover again, and turn on dry nitrogen. And I set the spectrophotometer to scan every minute. So it'd run a new curve every minute, plotting it on the same chart. And so you would see the edge, and as it dried out, the edge would shift. If there was any absorption or any porosity to allow it to shift, it would shift. So in about 15 minutes, it would stop shifting. I will have dried it out in this dry nitrogen. Now, there's certainly a lot of people who argue, well, that doesn't do this and that the other, and it's not dealing with that dot H2O and stuff like that. But it told me whether my coating was dense enough or not. And it took half an hour to do it or less.